let's have a review of the vision transformer backbone. For vision transformer, it takes an image as input. For example, the image has a dimension of 224 by 224, and there are 3 color channels, RGB. And then we partition this image into non-overlapping patches. So the input image is 224 by 224, and if each of the patches is 16 by 16 pixels, then there are 14 by 14 patches. Altogether, we have 196 patches in this image. Each flattened patch, because they consist 16 by 16 pixels, and each pixel contains 3 number RGB 3-dimensional vector. So altogether we have a feature vector of dimension 768. So we have a tensor like with this attention. B is the batch size. Then we have 196 patches. Each patches is represented as a 768 dimensional vector. We feed this input through a linear projection layer. Then we get a patch embedding. So also token embedding. This is so this is the embedding dimension. We can select this dimension to be any number we like, but here we choose this D to be equal to 768. This does not have to be equal to this. It's just happen to be equal in this case. So we get this patch embedding. So for each of these patch embedding, we need to add a positional embedding to indicate the position of the image patch in the original image. For example, this one indicates this patch is on the top left corner of the image, and this patch 2 is the next patch, is a patch next to the first patch. So this number 1, 2 is not like directly the number 1, number 2. This positional embedding is represented as similar as a patch embedding. That means it represents the position is represented as a 1768 dimension vector. Also, we prepend a CLS token, which is also represented as a single 768 dimensional vector, and we also add a positional embedding 0 to differentiate these CLS tokens from the rest of the patch tokens. So we have for all of the batches in the input, we have one positional encoding to add to the CLS token. Then we have the rest of we have another 196 positional embedding to add to the patch token. After add the positional embedding, we get this dimension. So we have B is a batch size. We have one CLS token and 196 patch token, and each token has a dimension of 768. We feed this into a transformer. Basically, the transformer didn't change the tensor dimension. So if we feed this in, we will get exactly the same dimension out. From this output, we extract the CLS tokens, which is a single 768 dimensional vector. Then we feed these CLS tokens through multi-layer perceptron. And depend on the number of the classes we want, we can project this from the embedding space to the class space that we want to do the classification task. So inside the transformer encoder, we can take a detailed look of the blocks. So we get this input to the token, the CLS token and the patch token as input to the transformer encoder. Then it passes through a normalization layer. Then for the same input, so the input is represented as X. So by project the same input with different linear projection, WQ, WK, WV, we get Q, key, V with respect to query, key, and the value. So we get three different matrix. So all of this Q, key, V has the same dimension as the input. Then for multi-head attention, we partition the feature space. Feature space has a dimension of 768. We partition this feature space into 12 subsets. Each set contains 64 features. Then we come to a attention calculation. So attention was performed according to this matrix. So basically for each query, we needed to calculate the similarity of the query between the query and the key, use a dot product. Then we use this similarity, we pass this similarity through a softmax function and use that as a weight to use that as a weight to multiply with a V, so that with a V vector, value vector, so that we know that according to the similarity between query and the key, we can assign different weight to the corresponding value. So for query, like we know that it has a dimension of 197 by 40. 197 by 46, and also for the key is same dimension, but here is a transpose, and we have 64 by 197. If we multiply these two matrices together, we get 197 by 197. Then we need to multiply with a V value. Value have this dimension. If we multiply these two matrices together, we basically get this dimension. So this is a this is a attention calculation. After we get this, we put it back, we merge it back into the feature dimension. So 12 head, each head has 64 features, then we merge it back to be 768 dimension features. Then we pass, of course there is a residual connection, then we pass it through a normalization layer. We feed it into a multi-layer perceptron, which contains two fully connected layers. the first layer up project the feature dimension by 4 times. Then the second fully connected layer project back to the same 7 input feature dimension. So this is a transformer encoder. So basically we see that the structure of this is use vision transformer to get patch encoding. Then after the transformer encoder, we get this, we get a CLS token plus patch token, but we didn't use the patch token. For training, we only extracted the CLS token and feed this into multi-layer perception. CLS token is what we used to train the network. If we have ground truth class labels, then we can calculate the loss functions and back propagate through this part, but we didn't use patch encoding during the training process.